Hello everyone, this is Tara Prabhakaran from Indian Institute of Tropical Meteorology, Pune. You can see the CAIPEEX team in the backdrop of our institute and the field site behind it. And these are the happy faces behind this particular program. I am indeed indebted to Martina, Odran and Greg for this giving this opportunity to talk. So the CAIPEEX has it's a program with two major goals. One is to understand the cloud and precipitation microphysics and to investigate cloud seeding scientifically. The program is funded by the Ministry of Earth Sciences and conducted by IITM Pune. The tracks shown on this image here, these are the places where aircraft has flown in many places in India in several sorties over the years. The uh, the CAIPEX missions are conducted over several years indeed. So why we need why we need this CAIPEX? Actually, there was a lack of cloud microphysics observations over India, and there were increasing demand for rain enhancement projects over the region. So why that rain enhancement project was happening, you can see the picture here where we are seeing the IPCC AR6 report on the water scarcity over the region. There are nearly almost throughout the year there are water scarcity issues. The region that I have encircled here, this place a major observational campaign took place where there is a water scarcity of every once in every 3 days only water is provided to the locality. So there are imminent problems, and we needed also to investigate the unconventional ways of water resource development programs. So the government has funded this program, and also we needed to improve the physics in the models, such as the cloud, aerosol, and precipitation aspects in the model. So before going ahead, I just want to give a little bit introduction about how the rainfall in India varies in India, especially the rainfall map shown here. It is actually the rainfall in millimeters per day at different locations, and we can see that there are some places get more rain and some places don't get more rain. This is during June to September, that is the monsoon period over India. So the actually there are different drivers for this monsoon. The point is that rainfall comes in. Also, you can see that in these plots where here we are looking at the time and the latitude plots where the rainfall does not come all of a sudden everywhere. There is a particular pattern, and also there are breaks in the rainfall pattern. So this is actually these periodic patterns are driven by the large scale circulations, and there are two different jets. So one is the low level southwesterly jet and the upper level easterly jets. These are indeed very trivial in contributing to moisture incursion over the region and making more rain. So while the monsoon is active, we can see that these are the aerosol number concentration observed at our site. You can see that the aerosol also get washed out, mainly all wash out, as well as there will also be less sources present, for less burning and other activities are present over the region. So every year these patterns are repeated, while each monsoon is so different, and which enhances scientific temper to chase monsoon and predict it well at all scales. So IITM was constituted in the 70s. Actually, we are supposed to do research on tropical meteorology, and we have a very big thrust on cloud physics and processes. So even before IITM formed, there were very many researchers going on in rain and cloud physics, as well as laboratory studies also started. And IITM conducted, since its inception, IITM conducted a 11-year-old cloud seeding experiment, and very many fundamental studies also came out from IITM during this period. And then CAIPEEX started in 2009, and we I just want to give you a bit more idea about what the main two objectives were pictorially given here. One is to understand aerosol cloud precipitation interaction, and the other is to understand and form a scientific basis for this rain enhancement projects. So the experiment was conducted over several years, and several airborne campaigns in 4 phases. And initially we have targeted scientific objectives on cloud microstructure, found some clues on the cloud properties, precipitation formation, and formulated a hypothesis and protocols to conduct the scientific investigation of cloud seeding in convective clouds. So over the years, there are array of studies that came out from CAIPEEX, and I have not included all the publications due to space. Only some major ones are included here. However, significant effort was needed to make this consistent and ongoing. So the CAIPEEX phase 4, as I mentioned, was very well planned and articulated to look inside the clouds before and after seeding, and tracking them with radars, aircraft, and also registering the background conditions of thermodynamics, surface fluxes, also rainfall on the ground. And we have indeed set up a laboratory in the dry region in the peninsula with water scarcity problems, and region was getting water every 3 days, as I already mentioned. And we set up aerosol laboratory, radar and profiling systems, and precipitation monitoring, etc., as shown here, several of the instruments shown here. And these are the 2 aircraft used in the experiment. With that being a dry place, we may not find any clouds there, but to our surprise, almost every day we were having plenty of clouds, which are having bases around 1 or 1.2 kilometers, or even little higher, and the freezing level was around 5 kilometers during the monsoon, and sometimes these clouds are going up to 7 to 8 kilometers with a warm region, a deep warm region, and a mixed phase region. So the aircraft, Beechcraft aircraft, was used as a research aircraft, which was going up to 9 kilometers, and the Beechcraft C-90 was used as a seeding aircraft, which will climb up to 4 kilometers. So the array of instruments used on the aircraft is shown here, and we have a temperature up to -22°C. We could register the properties of clouds and precipitation, and typically with an endurance of 5 hours. This is a typical cloud pass during our experiment, near to almost at 6.5 kilometers in developing convection, and you may see some dropel as we go deeper inside the cloud, and then water drops are also there. So actually done. This kind of cloud penetrations were done almost 5,000 times in the phase 4 of our experiment. So we have registered many cloud passes in different parts of convective clouds. So as it comes out clear, the water evaporates near to the cloud edges, and you can see the type of monsoon clouds present there. And in addition, we had many flights observations done within 100 by 100 kilometer area. So we can see that almost all the flight tracks are within a short period, short region, and these are indeed many cloud passes overlaid on each other. And it's also to be noted that this is because our rain gauges were rain gauge network was also located in that region. And you can also see the seeding locations with the red and blue circles, where which was all quite randomized experiment was conducted there. And I also want to show something very interesting here. If you look from below, how a cloud seeding event will look like. So this is from the ground we have registered, we could see, and you can see the aircraft going around the near to the cloud base, and you can see the plume
That's a
in
cumulus cloud.
yeah, it is going around, and we can see that the seed particle is getting dispersed. It also gives us a perspective on the size and the problem we are investigating. This is not that simple. So actually the aircraft made such round tracks below the cloud base once a seeding target is identified. And we can see the seed material is spreading around that region. Okay, so we had nearly 6 components to the program as indicated here, and these include the background observations, the background observations, the characterization of the aerosol and seed particle spectra, and the physical experiments with the radar, as well as the in situ measurements and the aerosol physical and chemical characterization, and the seed particle signature tracking within the cloud, which is done with a CVI inlet and with AMS and ASP2 instruments on board the aircraft. And also numerical simulations were done simultaneously, and we also done the randomization experiment, which resulted in 151 seeded and 125 not seeded cases. The results of this experiment is reported in the BAMS paper. You can scan it and get access to this. And what it really we see in terms of the cloud microstructure is shown here. So the cloud mean volume diameter from the three probes, that is the CDP, SIP, and PIP probes, approximately for the cloud drops, drizzle, and the raindrops are shown here. And the freezing level is marked here. So in the peculiar aspect of these clouds are the deep warm layer, and which is quite much deeper than 1 kilometer, and these are indeed actually indeed good for the droplets to grow. And one of the years considered here is dry, which is that blue in color, and the other is more wet, so the differences are also seen here. In other way, if we look at the vertical structure of these clouds with the maximum liquid water content in many research flights, so we can see the maximum liquid water content is sometimes reaching to 3.5 gram per meter cube, and which is quite comparable to several other tropical convection like made at different places. So this is also another important finding. Then if we look at the deep convective clouds at the end of the campaign, when the atmosphere was becoming drier and drier, and we could see more ice phase is produced, and radar hydrometria classes are showing rather convincing signature as in the in situ measurements. We can see the initial early stage of the development, it is the gropel, and then ice particles, aggregates, and then drops by melting of ice. So this structure is quite nicely coming up in our radar as well as in situ measurements. In the stratiform clouds also we had some observations, and we can see from the radar as well as radar hydrometeor images, as well as from the in situ hydrometeor images at different temperatures from -17 to 2 degrees. We can see the melting layer very nicely documented, um, with the snow melting, and one important aspect is these clouds were having also some ice water content and liquid water content at all these altitudes below the freezing level. So the mixed phase monsoon environment is very, very much clear in our observations. And I just compared that supercooled liquid fraction with some of the other published literature from Storwell-Moe 2017. So this is how it compares in our temperature ranges. And relating the subcloud aerosol to the droplet number concentrations, also we have seen some remarkable signature in comparison with the Indo-X observations. And continental effects is very clear here with less activation. So going further, we can see that there is a good concurrence between the subcloud CCN at 0.4% supersaturation and any other cloud base and the droplet number concentrations. However, interestingly, there is a large number of submicron and the submicron mode that is indeed acting here, and which are not that suitable CCN. So having done investigated on the background aerosols and the CCN activation, we also looked at the seed spectra, how it is how the seeding aerosols, how they are activating. So we have done a dedicated experiment with the two aircraft, one following the other and one sampling the other. So this was a phenomenal experiment. So we came up with some interesting features that the aerosol concentration in the background, in the exhaust, and the two flares or four flares, how good they are. Two or four flares, so we found nearly not much of a difference, while the activation diameter is also slightly reduced with so the hygroscopicity is indeed these aerosols are more hygroscopic that we found. So these seed aerosols are so also we have studied their size distributions, which I'm not showing here. Another important point is the cloud residue analysis. We have a paper in AMD on that by Mahin Konwar. And we used a CVI inlet with the MS instruments on board, and showed the signature of the chemical signature at different altitudes. So we could see that we could indeed trace these particles up to as high as 3.4, or in a growing convective cloud. So the results were compared for seeded and non-seeded clouds, and the size spectra showed a very consistent behavior of more larger size drops in the observations. And while coming to the result of the randomization, actually we have selected the randomized seeding cases with certain criteria. This was based on what we learned in the previous CAIPEEX observations. One was a very well-defined cloud base with no precipitation at the time of seeding. Other was the high liquid water content at 300 meters above the cloud base, and the updrafts, stronger updraft regions, and the warm layer depth, that is the cloud, the freezing level minus the cloud base height, which is more than 1 kilometer, and mid-tropospheric RH is more than 40%. So with this, we have got 122 non-seeded randomized cases and 151 seeded cases, and we can see that the seeded cases, clouds are not evaporating, or they are not dissipating as much, but in the non-seeded cases more evaporation is happening. And also the way, if seeded early in their life, they are indeed making rain. So there is rain in all these categories, while there is not rain in the other categories. So the further vertical structure of the cloud also was investigated with the radar, polarimetric radar observations. I am only showing the reflectivity in the seeded. There are many cloud samples with the seeded and non-seeded in an area. And the differences, we can see that larger drops and more rain. So larger drops, more rain at the surface are in these CFAT diagrams. We can see that. So now, then we conducted a different type of statistical analysis with the percentiles, which showed a consistent behavior of relative enhancement of rainfall from several seeded samples. And you can see the number of samples considered. These are the percentile analysis of the relative enhancement factor. And in all the cases, we can see a higher relative enhancement in this accumulated rainfall. So this also showed a positive impact. Then when we come to, there were also clouds grouped on the basis of reflectivity at the time of seeding. This is the time of seeding. If the reflectivity is below 30, actually we considered they are not matured clouds, and here the reflectivity is above 30. So we did a quartile analysis where you can see the reflectivity peaks a bit later in the seeded category compared to the non-seeded category. Non-seeded category clouds are dissipating very fast, and they are raining out fast, but seeded category, they last longer. So 20 minutes more they lasted. And these clouds we considered here are only isolated convective clouds. There were no we have not considered the merged clouds in this particular analysis. So these are also part of the randomized sample, where seeded clouds and non-seeded clouds were done in a random way, randomly seeded. So I'm sorry about the quality of this particular figure, but the message that I want to convey is that the aircraft observations of seeded and non-seeded samples near the cloud base before and after seeding. Actually, we made a cloud penetration before seeding, and we made a cloud penetration after seeding. So you can see the difference in those non-seeded case. There is no seed material within the cloud. In the seeded case, there is seed material in the cloud. So the droplet number concentration of less than 20 micrometers size, actually, which reduces, while droplet number concentration above 20 micrometer actually which reduces, and the droplet number concentration less than 20 micron increases in the seed sample. So it is vice versa in the non-seed sample. So in addition, there are few other factors that can be noted, which is the reduction in the supersaturation being consumed in the seed sample, while enhanced spectral width were broadening of the spectrum, but it is broadening towards the smaller sizes, reduction of the size of the droplets. So these were indeed were part of our hypothesis, and so we hypothesized that as we seed, the droplet size would reduce, number will increase of the small size, and they grow slowly. Our hypothesis was to delay the rain formation, so that the cloud grows beyond the freezing level. So that was indeed our idea, and which we were able to simulate as well as observe with the radar and in situ measurements. So this brings us to a point to think: is there any aerosol invigoration in these clouds? And we have looked at quasi-steady supersaturation in many cloud samples, and the vertical variation of the quasi-steady supersaturation is shown here. The color is indicating the liquid water content, and also the clouds are segregated into low, less than 500 cc, and 500 to 1500 cc, and more than 1500 cc. There is still high supersaturation in the moderate case. You can see this is very high supersaturation in moderate case, polluted case. This moderate pollution, what I am talking about, is much higher than the pollution, the concentration levels noted in other places. So this further is shown with the PDF plots, where here you can see that the very clean cases, the supersaturation indeed it has a tail, but in here again clean as well as the polluted cases, the tail is quite significantly large. And so this is there are many clouds considered here, so it's a significant result. And also looked at the precipitation in those cloud samples with the precipitation imaging probe. The mean volume diameter of the precipitation drops are also looked at, and we can see that with the increasing, we have seen some larger drops in the polluted clouds as well. So that brings me to another related why are we really seeing these large drops, or why are we there is some consistent behavior. So are there any signature from the radar observations? Because radar observations we can show for many clouds, but in situ measurements, even one can say, okay, it is depending on the where the stage of development of the cloud you have penetrated, or many complexities are there. So from the radar observations, here I'm showing the reflectivity on the top of one cloud, and at the bottom the specific differential reflectivity, which we can indeed get as a signature for the supercooled liquid also here. So what we are seeing here in this animation is that clouds are moving from west to east. They are invigorating as they come over, and they're also making, and similarly we can see some liquid the enhancement in the KDP at the higher altitudes, and the clouds are staying until the KDP is exhausted. KDP is indeed the liquid water content is exhausted. So is it so that the more liquid indeed present there is indeed invigorating this convection, and is it something that sustaining the cloud further? I think this needs further investigation, and our research continues that way. And the seeding experiment what we used here, it is actually it has been a research study. So it gives us immense opportunities to explore more and see whether we can really make some of these underlying problems we can address with the observational data. So now I come to conclusion here, where I want to say that the CAIPEEX is one of the most comprehensive experiment on the cloud microphysics over India, and a systematic approach to investigate hygroscopic seeding was attempted with physical and statistical and also numerical simulations. Numerical simulation results I have not presented here. There are plenty of papers we have addressed these aspects. Even seeding simulations were also conducted, and also CAIPEEX gives the highest number of randomized cases in the convective cloud seeding with physical investigations as well as statistical investigations at a catchment scale. Which I think it is very phenomenal, and it is demonstrated that the seeding signature can be traced within convective clouds. This was actually a big problem. Whether the seed material is really entering the cloud or are we getting some other signature was not quite known. Now we could trace the seeding signature along with the microphysical changes, which is important in these clouds. Also, I want to say that CAIPEEX is only the beginning for more exciting cloud physics research in India. Actually, our government has recently funded a mega mission Mausam project. In Hindi, Mausam it is the weather, and which is centered around improving high impact severe weather prediction. And now we know we need to address this, and actually everyone should be aware of the bad impact of weather, and early warning should be given. So there is a significant thrust on that particular topic. And so in the mission Mausam, there is also a thrust on understanding clouds and study weather modification prospects. So because it would be required in the future, so there is a like what are the protocols for any weather modification experiments, and how can we formulate them scientifically? That will be the thrust. And we have formed a center of excellence for cloud physics and weather modification research at IITM. And it is actually we are in the plan to develop a convection cloud chamber in that center, and it is to foster cloud physics research studies. And the laboratory, airborne, and the ground-based observations and facility development and research will continue to happen along with the targeted numerical studies. And I'm very happy to say that there are plenty of opportunities for collaborative research. We will use almost all of the observations that I have mentioned here to better our models, to do something innovative and exciting, and for the good for the humankind. And this is a sketch of the mission Mausam. And yeah, it is not only about with the atmosphere. We also should know what is going over the land, but also we should know about what is going on over the ocean. So it's an integrated mission. So initially it is for 1.5 years, then it will be expanded later. So this is where we are currently, and looking at and looking for greater opportunities and greater science. And I want to thank you all for listening, and thank you ICCP for giving this unique opportunity. I also want to thank Martina, Udran, and Greg, and other members of ICCP Commission. And I also want to thank specially to Andrea Flossman and Darrell Baumgartner for quite a bit of mm, learning curve I had. I'll, I also want to remember many other colleagues whom I have not mentioned here. Duncan and many others who has been very instrumental for making like in our learning process, and we are very grateful. And I also want to welcome everyone to WMO Scientific Conference on Weather Modification, which is going to happen in IITM Pune, and also the MECA ICCP 2028. Thank you all, and thank you all for listening, and I will take questions. Thank you.